You can write this down. Got that? Okay. So let's just check what vocabulary you know. So what is uncertainty?
Error.
Yeah. No, it is like an error, but how could we be a bit more precise? Like, when do you use it?
Like a possible value that could be.
Yes, good. Monica?
When you don't know what factors could
Good if you don't know what could affect the effect of what, though. We've not said that. The measurement, okay. So we have this in our head that we use some machine, whatever it is, voltmeter, clock, meter stick, whatever, and this performs a measurement on something we're looking at in the real world. Look, this represents the real world, and this represents my measurement, and here's me. So we understand, of course, that whatever we're measuring, there's a true value it has. But when we make that measurement, we don't really get the true value because it's not the exact value. We could have made a mistake. The machine could have made a mistake, or whatever the factors are. So we use the machine, and then it gives us back a measurement. So, for example, maybe we'll do this once, and we'll call the first value we get x1. Now, you might say, well, that's okay. I wanted to know what x is, and I measured it, and I got x1, and I'm finished. I'm like, well, not really, because maybe there was a big problem, and this value is totally off. So maybe you should measure it again. Or maybe you should even measure it again. And of course, you get the idea here. The more you can measure it, the better. But what do you do if you have many, many measurements of x? So for example, let's say you measure x n times. What's your best estimate of x?
Average.
Yeah, but which average? It's called the mean average.
Divided by.
Yeah, which we represent with a bar on the top,
Yeah.
which is simply you add up all the values of x and divide by n. This is our best estimate. Now this is obvious, but maybe this isn't the best estimate. Maybe there's something else we can do. Maybe if we have 10 measurements, maybe there's some way to put these 10 measurements together to get a better answer. So in fact, it is actually a theorem. It is actually a proof in statistics that, believe it or not, this is the best way to put these 10 measurements together to get one measurement. This actually is a statistical proof that this is the best way to estimate it here. So that's fine. So now we have our estimate of x. We say that x is roughly whatever we got when we had the average. But you realize, well, if we keep doing this, we keep getting different values. So it'll be wrong it's wrong for me to say x is equal to x average, because each time you measure more and more, it changes a little bit. So what we can say is x is roughly the average, and then this is the idea for the lesson: plus or minus some uncertainty of x. So for example, if this was measuring a height, maybe you might say the height of John is 1.6 plus or minus 0.002 meters, as an example. Yeah? What?
Still, why should we suffer from error of machine? There should be exact height, right?
Yeah, there is an exact height. That isn't the problem. The problem is finding the exact height.
So the machine is proper.
Stop.
Not the machine, the person who operates the machine. In physics, it's quite difficult. I mean, it's impossible to get an exact measurement, that's a fact. No matter what you do, every measurement has an error involved. And the reason is different for the measurement. So like, in the case of the height is probably something you could measure quite accurately because you could bounce a laser off the person. But you realise, well, it doesn't. People's height changes slightly as they stand. It's not like it's a flat, you know. Even just breathing in and out means each time you measure the height, it's slightly different because if the person is breathing in, maybe it's 10 micrometers higher. You know, so you can never be exact. And this is the thing I said. If you only learn one thing about the labs, is that every measurement has an uncertainty with it. Okay. Can I continue? Yeah. Did you write this down? Yeah. Okay. So the best estimate is the average, the mean average. Fine. But now on to uncertainty. So just to be clear, what exactly what do we mean when we say the uncertainty of X? So what would you say it is if you were to give it a definition? Yeah, but even error doesn't tell me what it is. Like if I gave you a number, what does that number mean? Yeah, it's kind of like it is kind of like bounds, isn't it? But you realise you could do something silly like say, oh, the height is 1.6 meters plus or minus infinite meters. Now this doesn't quite seem right because there is no limit. So what we want to do is we want to try and balance two things.
Yes.
Even when we put the limits on the uncertainty, it's still possible that the true answer is outside these limits. That is the fact. You might calculate, oh, the height is 1.6 plus or minus 1 centimeter. And it's possible that now not likely, but it's possible that you're outside the 1 centimeter. So do you understand? You have this balance here. Look at the different situations. You could have 1.6 plus or minus infinite meters, or 1.6 plus or minus 0 meters. Now in this picture here, you will be 100% right. It is true that his height is 1.6 plus or minus infinite meters. There's no height he could be that's not included in that. But although it's 100% true, it's 100% useless. Now you could give this one here, this will be 0% true. His height cannot be exactly 1.6 meters. That's impossible. It has to be 1.6 and something else. It can't be exactly 1.6. That's actually impossible. And so although this is 100% wrong, it actually is more useful because now you actually have a number that you can say his height is. So there must be some balance in between. And the balance is different for each course. So for some courses they use one level of accuracy, and for some courses they use another level of accuracy. For this course I will use a 50% rule. That means I want to put limits on my measurement so that I should be right at least 50% or more of the time. So the UX puts limits, or another word for limits is bounds, on X average so that it is at least 50% likely the true value is in the limits. So for example, e.g., if I say he is 1.6 meters plus or minus 1 centimeter, then I'm saying that I'm at least 50% sure that his height is within these two ranges. So I've got a 50% or more chance that his height will be between 1.61, 1.59 meters. That's what I mean in physics and in this class when I say uncertainty. Some classes they want you to use a higher level of certainty, a higher level of confidence. So at university, they will want the limits to be 97% confident that you have the right limits. And in fact, there's a very easy way to do that. If you want to be 97% confident, believe it or not, all you have to do is just multiply this by 2. So, if I do plus or minus 2 centimeters, I'll be 97% confident that his height is within these 2 limits. But that's much more detail than we need for this physics assignment. So this is what I'll say the definition is. Yep.
I was thinking, if you try to run 26 plasma advantage and you fail the possibility the answer will be outside 1 centimeter, then why not just say 2 centimeters?
Because even at 2 centimeters, it's still possibly outside it. Because at 2 centimeters, you're 97% confident. And yet, I get what you're saying, so why don't just pick a number so it's 100%? The way the mathematics works is that as you have more multiples, you never reach 100, you only approach 100. So when you use 6 multiples, there's still a 1 in 1 million chance that you're wrong. So the only way to be 100% sure is if you use an infinite number, but then that becomes useless then. Yeah. In engineering, where safety is vital, they will use a 6 multiple to make sure the measurements are within the necessary limits. So if you wanted to build something that can withstand a certain force, then you might want to use a 6 multiple to make sure that, okay, what I have is definitely in the right zone. But for us, we're not, nobody's going to die if we get this wrong, so we'll just use this definition. Okay, I take it this is new information.
Yes.
Yeah, in chemistry you keep saying error, so in chemistry you simply call this the error. And that was it. Okay, great. So, now that we have an idea of what uncertainty is, we would like to calculate it. So I have 4 methods to calculating the uncertainty. So the first method 0. So, may I ask, how many methods, if more than one, how many methods did you use in chemistry to calculate uncertainty?
4.
Did you really? If so, tell me them. No. That's not 4 methods. I want, for example, the plus, you only learned how to do it one way. The minus, you only learned how to do it one way. Yeah, well, that's what I mean. Like, it's not like you got 2 different formulas for plus or minus. So you have one formula, although it's a different formula for each situation, and in each situation there's one formula. So I shall give you different methods. So the first method, method 0, is one that you shouldn't really use. This method, what you do is you guess. No.
You mean guess the
Guess the uncertainty. No. You're not guessing the measurement.
You guess the answer.
You're guessing the uncertainty. No. You see, you're thinking about it too much. It really is your best guess at what you think the uncertainty is. In some situations, this is the only thing that's possible. Like, if you're talking about some sort of distant galaxy, and you're trying to measure if there's oxygen on the planet, I mean, how else can you get the uncertainty unless you guess, Now, when I say guess, I don't mean a total guess. Use your best logic to try and guess it. But it's a fine method. I mean, sometimes you need to do this in physics. So on to the first real method.
Yeah.
Guess again. Method 1.
Look at the label.
Yep, correct. That is this. The first method is, you have two choices. You can either check the machine to see if there is a reported uncertainty measurement on the machine. Now, most lab equipment does have printed on it its accuracy, the uncertainty. If it doesn't, then the rule is you use half the smallest reading. So, for example, if you're using a clock, e.g., and the clock is 2, if you're using some, like for example, when we did the Newton's experiment, you were measuring the speed. Well, because there's only 2 decimal points, then you would say here the uncertainty in x would be 0.01 over 2. You use half the smallest reading you can make. Or you can simply check what it says on the machines. The machine might say plus or minus 0.0, no, it'd be 0.5 seconds. You know, might say this on it. Yeah. Since you knew this, were you just being a wise guy, or you were told this in chemistry?
I'm a wise guy. And I was
Wise guy is a bad thing, by the way, not a good thing.
I was 20.
Okay.
And I'm a wise guy.
Okay. You know what wise guy means, don't you?
I don't.
Okay.
In a special way, no, I don't know what does that mean.
Yeah, know it all. Yeah. Okay, can we go on to the next method now? Yeah. Right, so that's 2 methods. Now on to the next one. Does anyone know of any other method?
Ask teacher.
Sorry, that is not a valid method.
Calculation.
Yeah, this second method, this third method, which I call method 2, you can only use this if you have 2 measurements. And this is kind of like what we talked about when we were doing Snells and ohms and so on. So if you have 2 measurements, the uncertainty for the x, the bigger measurement minus the smaller measurement over 2, or the max minus the min over 2. Now this only works when you have 2 measurements, of course. And lastly, method 3.
Google. I'm serious.
Dude, stop saying stupid things, please. Thank you. Method 3 is when you have a list of measurements. Maybe you did the experiment 10 times. So, in this one here, you can get the uncertainty. What you do is you calculate the difference between each measurement and the average, the absolute difference. You add up all these differences and divide by n. So in other words, it is the mean, average, absolute difference. You know what I mean by absolute? The positive difference. Oh wait, oops, sorry. Huh?
They're all.
The
You add all of them and then you subtract the others.
No. If you have, for example, let's say 1.6, 1.8, and 2, what you do is you get the average. So the average here will work out to be 1.8, and then you look at the difference between each data point and the average, and you average those differences. So it's the difference between the data and the average. Add them all up and divide by how many you have. And it's very important that you add positive numbers. That's why I have these brackets here. So it's the absolute difference, the positive difference that you only care about. And the reason for that is because uncertainty cannot be negative. You can't have a negative uncertainty. It's always a number more than 0. perhaps it's worth saying. Note and remember, uncertainty of x is always bigger than 0.
Teacher,
Yeah.
what is the measurement? I mean the instrument. What do you know? The instrument is not good. Like.
But that's fine.
Scale, it can only be 1 kg.
It can only measure in 1 kg.
It can only measure 1 decimal place.
Yeah.
And all the things will always be the same, so there has no uncertainty.
No, like imagine it could only measure 1 decimal place. Then if you perform one measurement, the oh, I see what you're saying. If you keep measuring
the same thing.
Yeah, so in that case it's
0.
No, I get what you're saying. I think the way you need to think about this in your head, I didn't actually make that clear. Can I scroll down? Yeah. That's a good point actually, Lee. So you have your methods 0, 1, 2 and 3, and the idea is you can always use 0. The question is, can you use 1? If you can use 1, you should. You can always then use 1. If you can use 0, you ask, can I use 1? Then when you get to 1, you say, can I use 2? And when you get to 2, you say, can I use 3? So in your example with the weigh-in scale, can you guess the uncertainty? Yes. Can you get the uncertainty by saying it's half the smallest value? Yeah. Yeah, because in Lee's example, it was like 1 decimal place on the machine, so it will be half the smallest value. In this one here, can you do the 2 measurements added together and divided by 2? Well, you can't really, because there is no min and max. Because in both cases you get the same reading. So in that example, you would have to draw the line here and say this is the best you can do. So in a perfect situation, you would like to make it all the way down to the end, because this gives you the best estimate of the uncertainty. So it's kind of like a tree or like a progress. You want to go as further down the methods as you can. Okay, continue. Yeah. So back to here. That's all fine. But of course, in real life, you're performing a measurement so you can know something that may be combined more than one measurement. So, for example, if you want to measure the area here, you don't take out your areometer and set it to meter square. All right? Do you have any machine called an areometer? No, of course not. How do you measure area? Yeah, you would have to go measure this side, and then measure this side, and then you get areas xy. Now you know the uncertainty of x and you know the uncertainty of y. The question is, can you know the uncertainty of a? And the answer is yes, of course you can, but it's not. They don't combine in the way you might guess. So the uncertainty of a is not the uncertainty of x times the uncertainty of y. Yeah.
So you know what? We have that thing.
We have that thing.
That's a real thing?
It's a real thing.
Dang.
But inside the water.
For water?
Yeah, then you meter actually what they call
no.
meter.
No, this is for paper, we'll say. So you need a paper areometer. So I guess you can't just stick meter at the end of something and...
Google it to prove you wrong.
Yeah,
I was wondering if there's something like that.
Yeah, as I was writing, I was thinking, I bet somebody made something like this.
Yeah.
Anyways, it sounds like you know the combination rules already. So let's do it as a revision then. Can I scroll down here? The first one is you have Z, which you want to know what's the uncertainty of Z. And the way you find Z is you add 2 measurements together. You measure X and then you measure Y and you add them together. So what is the uncertainty of Z here? Yeah. Roughly fact, it's not exact, but roughly it's the uncertainty of x plus the uncertainty of y. Oh, sorry, I used delta by mistake. I have to get out of that habit. We use u in physics. Okay, that's fine. And interestingly, if you minus them, the uncertainty is still added. Okay, now on to the juicy one. If z is equal to x multiply y, what's the uncertainty of z now? There's a root in it.
X squared.
ux
Mm-hmm.
plus
Nearly. Nearly.
minus.
No.
Um,
First you have uncertainty of z, or not the average z value in the front here. And then here, there is, you're right, it is a square, and it is a square. And on the top here is uncertainty of x over average x value, and then uncertainty of y over average y value. Now this might remind you of the formula in physics, in chemistry, for calculating the percentage, what did you call it, percentage error or fractional error? Or yeah, but how do you report error, as a percentage or as a...
we find error and then we find relative error and then type of percentage error.
Yeah, so I think the one that's similar that you've seen before is the relative error. Is relative error the error over the...
Error.
Yeah, but is it the x uncertainty over the average x?
I check mine.
Or is that percentage error times 100? Anyways, it's similar to one of those ones,
Oh,
okay?
relative error is like the error times the smallest value.
Ah, no, it doesn't matter. Anyways, Lee, x over y, the uncertainty of z is equal to the average z. It's the same thing. There, and there.
Can you do the same thing?
What do you mean, how can it be the same thing? Weren't these two the same?
Yes.
So, why didn't you ask me how come they can be the same thing?
Okay.
No, don't be so acceptant. Tell me what your logic is.
No, I just have like a memory that they are different. When we are in chemistry. I'm not sure if they're correct.
If you have your notes, that'd be wonderful.
I have in my room.
Continue.
6 less than 5.
No. We've done the four methods. They're finished. This is now a different thing. The combining. Can I go down to the next there's two more combinations. So the next one, which is a useful one for us, is what if z is equal to x n y m?
Okay.
Did you see this one in chemistry?
Yeah.
No. So the uncertainty of z will be the mean average z square root n uncertainty of x over average x squared plus m uncertainty in y over average y squared. In fact, it looks very similar. It's just the coefficients are n and m.
Oh, why do we prove this?
No. This is quite difficult to prove.
Yeah, we have to do this one. Like, you have an animal.
Did you do this one?
Yeah.
Which experiment?
Just of generalization. You are doing that chapter.
Yeah.
Got that? Yeah. Continue? Yeah? Okay. So the last combination one is, it's kind of a simple one. It's just if you have a measurement and it's multiplied by a constant, or maybe you have something complicated like z equals k, I don't know, x squared plus whatever, blah 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 blah. If you can take the k out, so if you can write it like this, z equals k blah blah, then you're allowed to do the same thing for the uncertainty. So the uncertainty in the z will equal k times the uncertainty in the blah blah. In other words, you're allowed to pull constants out of the uncertainty calculation. Which kind of, I think about it really needs to be like this, because if I said its height is 1.6 plus or minus 0.01 meters, if I change that into centimeters by multiplying by 100, then of course the uncertainty, all that should happen is it too, you multiply it by 100. Yeah. Okay, now before we do examples, the last rule, which is the hardest one, and in fact it requires it will require an Excel lesson on it, but I'll just give it to you since I'm giving you all the rules together. Can I scroll down? Yeah. So in physics, a lot of the time you can make graphs like this: x, y, point like this, and it's a straight line. But the problem is, because of your errors, not all the points line up. So you understand, of course, that if you did more experiments, you would get maybe more points, and this could perhaps change the line slightly. So in other words, the line can kind of move a little bit. And if the line can move, then what about the m? Then the m can change. Now, why do we care about the m? Because sometimes the m is something important, like the resistance, or something like this. So we would like to know, if we're using the m to calculate something, what is the uncertainty in the m? In other words, how much can the slope change? And the formula there is the uncertainty in the residuals of the y over the uncertainty in the residuals of the x divided by square root the number of points you have. And if you're thinking, what the heck is this? That is to be continued. That will be in the lesson where you bring your laptop in.
To be continued.
That's small.
Tomorrow we might do the experiments and then, yeah.
Wow.
Okay, continue. Yeah.
You need to do.
Yeah.
You need to do the uncertainty for all the measurements, like speed.
No. Well, for the lab report, I need you to do two things to the uncertainty. When you list the measurements, beside every measurement you should list the uncertainty. So, for example, if you say the U is 5.62 meters per second, you should include beside that plus or minus 0.005 meters per second, because the light gate, if you remember, has 2 decimal places on it. When you're listing the mass of the trolley, when you measure with the spring balance, when you think about that, you could probably only measure that, I think, to an accuracy of 50 grams, so it would be plus or minus 25 grams. So in other words, when you report measurements, you should have the plus minus uncertainty. And then at the end of the lab report, you're going to need to calculate the slope of the line, which will involve a calculation of this. Now, all of this calculation is done in Excel, which I'm going to teach you how to do in class. So once you know how to do that, you just have to change the numbers for your particular experiment. Continue?
No.
You have this? Yep. Okay. So let's have a look at some examples. So just to get started with, as our first example, let's think about something that you used. I'm trying to think of something in real life that would be good. Not a weighing scales. Nobody's talking about weighing scales in the class. Okay, I got an example, I guess. When you're waiting for the bus, it says how many minutes are left. Oh, no, I'm being serious. So, so when you're waiting for the bus, it will say on the board, 4 minutes remaining. Is it really exactly 4 minutes to the microsecond?
No, exactly.
No.
Really?
So,
Real information.
if you say the time is 4 minutes, 240 seconds, of course there's an uncertainty with the time. Now, this is kind of interesting. Which method should we use here? 0, 1, 2,
0, 1, 2, 3.
Which method should we use?
1, 2.
Well, definitely not 2, because you only have one measurement. It's not like there are two signs and one says it's 4 minutes and the one beside it says no, 5 minutes.
What?
So we kind of have two choices here. We can use method 0 or method 1. If we use method 0, then I would kind of say the answer is 2 minutes, because that's based off of my experience. You know, I think it could be off by 2 minutes, as much as 2 minutes. If we use method 0, then we would say the answer is what?
30 seconds.
30 seconds, half a minute. Because that's half the smallest reading of time you have. Which do you think is more appropriate to use in this one? Method 0, because the situation is informal, it's not an experiment. So we'll use the method 0 then. Okay, so that's our first silly example, if you can write that down. Can I just borrow a spare pen if anyone has one? Thank you. Yeah.
Did you put the text link on
I forgot to, sorry. I'll try to remember. I don't think I did, unless I was so sleepy when I did it, I don't remember.
Do you have it?
No, I said I'll put up the links for the tasks to upload them so I can check. I need to try and remember. Hang on, I'll make a note to remember.
I deleted the word. I uploaded it wrong.
Yeah, I think so. Yeah. Okay. Next example? Yeah? Please. Next example? So this is like question 1 then. Okay. Next one, question 2. Right, so let's do another example. So let's say you have 2 English teachers, and you ask each of them, what grade do you think the student will get? So the first teacher says, I think their English grade will maybe be a low 60. So they would say something like, something like 62%, 62 or 63%. And then the other teacher says, no, I think there'll be a high 60. So we'll say 67, maybe 68%.
That's it. They're all
That's true, but I would like to know what is the uncertainty here. So, have a think about that. What would you say it is?
0.
No, I think you're thinking a bit too much about this. So look, oh sorry, that's the wrong letter. Uncertainty in their, in their score. When the first teacher says 62, 63, a low 60, that value you use should be 62 because you're using the minimum. And on the other side you should use 68. So the difference here, this is 3, is it? Yeah.
Yes, true. Yeah.
So although so in other words, you're saying that you think the student will get a 65 plus or minus 3%, is what you're saying. Yeah. Yeah.
Where does 65 come from?
Average.
What? 65.
Continue. This isn't supposed to, these are supposed to be the silly, easy ones. We're not on to the real ones yet. Continue?
Yes.
Yeah? Okay. So, next one. Question 3. Now we need some calculation here, so this is more like a real one. So, for example, here, you measure a student's height using a measuring tape. You know, the wheelie ones. And you want to be accurate. So you and 2 of your friends measure it. So the 3 of you get. So let's say the first person does it, and they'll get 1.72 meters. That 1 point. That's a reasonable height, isn't it? Oh, is it? All right.
This is your hand.
Oh, you are proud of that.
Does that include the without the hair? Okay.
I don't have it.
1.73, and then the last one we'll say is 1.73 as well. So, what method would be the best method here for calculating the uncertainty?
2 to 3.
One can be possible.
Well, now, but remember the rule. If you can use 0 before you use it, you should ask, can I use 1? So, can you use 0 here? Of course. Can you use 1?
Of course.
Yes. But can we use 2?
Of course.
Yes.
What can I use?
Huh?
That's also one.
Yeah, but you can use method 0, 1, 2, or 3. In fact, for this example, you can use any method. You have enough information to use any method. Therefore, you use the highest method, which is the last one, method 3. Do you remember that formula? It's you add up the absolute difference and divide by, in this case, divide by 3.
Do that.
Do you understand?
Yeah.
Well, look, try it. See what answer you get. I'll do it on the calculator in a moment. What's wrong?
Oh yeah.
Got an answer, Kate?
This is the formula xi is in sum related. I'm going to do it.
Xi is each individual one.
Oh, each individual.
Okay, I better do this one since we're getting confused. So the first thing I want to do is get the average. So here, 1.72 plus 1.73 plus 1.73 divided by 3 and 1.7267. Okay, that's the average height. So now we would like to calculate the uncertainty in the height. And the rule is you have to look at the differences, the absolute differences. So the first one, how different is the first x compared to the average? It's 0.0067 different.
Yeah.
The difference between this and this. Yeah? Does that make sense? Now, the next one, how different is the next one? I need a calculator here to help me. No! It's 0.00 all the trees. .00 all the trees. And the next one is the same. And then we divide this by 3. So we get
0.004444.
yeah, 0.00445. I think.
6.
Yeah, I'm going to round this to 5. So the answer is 1.7.
267.
Yeah, 267. Closer. Yeah.
Whoa.
Average, the 1.7267.
Yeah.
Is it okay to use 1.727?
Yeah. Like there is people who say you shouldn't use more decimal points than is justified. So each measurement was performed at 2 decimal places, so it might be a bit unreasonable to use 4 decimal places here. So if you wanted to use 3, that's fine. And there are rules actually for how many decimal points places to use. Can I continue? Yeah. I can't remember right now, Monica, but I think there's some rule here. You see, each measurement was done to 3 significant figures, and I think there's a rule that says that the uncertainty that you measure should be at most 3, but I would prefer to use 2, because the uncertainty is even more inaccurate than the measurements themselves. So using the same number of decimal places suggests to the reader that you're as accurate there when really you're not. Because remember, we said the uncertainty, we only expect it to be right half the time at least, the bounds. Another example now? Yeah? So I think we're getting the idea here. So here is question 4. So in this example, a student is measuring the area of a box or whatever it is here, and they work out, this side here, I measured this to be about 1.01 meters plus or minus, and they think 5 millimeters. And on the other side here, they got slightly more, 1.02 meters, but the uncertainty they calculate, they think is also 5 millimeters. So they calculate the area, and the area is something like 1 point whatever meters, But it's not the area that I care about, whatever. Yeah, what I want you all to calculate for me now is the uncertainty in the area. Well, you can calculate the area if you like. By the way, how did they get the 1.01 to begin with? They probably measured the length many times and took the average. Okay, so this is already the x and this here is already the y calculated. In other words, in this example, you're jumping to the end. We imagine the student did some calculations already. Okay. Got that? Yeah? Guys, do we have an answer here? So, let's have a look. The formula I should use should be average A square root uncertainty of x over average x here, plus, and then the y over the y. Now this here is just the x multiplied by the y. So yeah, 1.01 times 1.02 square root that squared plus that squared. The first one is
1.01.
yeah, well let me just type in 0.005 over 1.01.
Yeah.
0.005 over 1.02. So 0.0072. That's the error here, the uncertainty. Yeah? So just one sec, you would say the answer is area is 1.0302 plus or minus 0.0072 meters squared. And 50% of the time you would be right. The true answer is between these two. Yeah? Yes. But you go backspace, is it?
I can hear. How come come here the average?
Because I tell you the average x and the average y. No, we times them. Area equals xy. Yes.
But why do we put in the area in the formula of the... nothing. Yeah, why are we putting in the area, the average area into the uncertainty. I mean, they
Isn't
should
that-
have no connection, right?
Isn't that the formula I gave you?
Yeah, but I just don't understand. I mean, the area is the area. I mean, the uncertainty is the...
The uncertainty in blank equals the average blank value and then the square root piece.
So not the inside.
This?
Oh.
Inside? What are you asking me? Confusing me.
And there is how to budget the phone.
Yeah, I don't get it. Why does it have the effect of the uncertainty?
Oh, why does the value of the area affect the uncertainty in the x and the y?
Yeah.
Because the area uncertainty is the thing you want to calculate. So, to me, it seems reasonable that you should know what the area is as part of the formula for calculating the uncertainty of the area. But the technical reason is it's a bit more accurate to say this. If you say FA equals the average of A, the uncertainty of A over the average of A, then this formula can be rewritten if you divide the A underneath as FA squared equals Fx squared plus Fy squared. In fact, what's actually happening behind the scenes is there's almost a Pythagoras theorem on not the uncertainty, not the average, but the ratio of the uncertainty to the average. So this appears because it was in the denominator here, and the reason this is in the denominator here is because the rule is kind of like a Pythagoras on the three things, the A, the X, and the Y. And you might say, why is it Pythagoras? And then this is where it gets complicated. I haven't explained at all where these rules come from because it's too difficult to explain. But it is a rule from statistics. But you're not happy with that.
But this is complicated. Like, if you use the same instrument,
Yeah,
and we measure it like the area,
yeah,
so the uncertainty get different every time we measure different things.
yeah. Huh?
Yeah, that's what the formula say. Like, if I measure
Oh,
the
yeah.
area of this row, and if I measure the area of this row, the uncertainty is different, even though
Yes.
I use the same instrument.
Correct, yes, yes. And the reason for that is for the same reason we're talking about uncertainty, is not only is the measurement something we cannot know exact, but the uncertainty is also something we cannot know exact. As ridiculous as that seems, not only can we not know X for sure, we cannot know how much we don't know what X is. So that's why the uncertainty is actually not really changing.
Yeah.
Like there is some kind of hidden uncertainty inside of the book, but our estimate of what the uncertainty is changes. For the same reason that the area changes, because we don't know how much we don't know the X. And this, by the way, this keeps going all the way down. So if you said, we don't know what X is, we don't know how much we don't know what the X is. We don't know how much we don't know how much we don't know the X is. This continues all the way down. There's no bottom to this. It's all the way down. Okay, this one is okay. You are unhappy conceptually with this here,
Yeah.
but it's a result of the fact that we also don't know the uncertainty accurately. Okay, next example. What one is this? Number 5. Okay, so let's make this a little bit harder now. Let's say I'm measuring something. It doesn't really matter what it is. I'll just call it X again. And let's say my measurement for X is, let's go with 2, what unit shall I use? I don't want to use meters again. Let's use,
Nanometer.
no, stop.
There is
I don't want to use
nanometer.
distance. I want to use something else.
Giga.
Kilogram.
Tera.
Graph.
Kilogram.
More.
Yeah, okay.
And then
Candela, we use candela, will we? Let's just go with joules. So 2 joules plus or minus, and let's make it 10 millijoules. And for whatever reason, I really want to know what y is, and I'll say y is square root x. So I know what x is, and I know what the uncertainty of x is, but I don't actually care about the x. Do you know what? The units are stupid. Don't bother writing down the units. Just say 2. No, I need to have units. Okay, no, do write in the units. 2 joules plus or minus 10 millijoules, and y is square root x. And I know everything about x. I think it's 2 joules, and I'm uncertain by 10 millijoules. But what I don't know is the y. Well, I know what the average, my estimate for the y is. I think it'll be about square root 2. So that's 1.4141 joules. But what I really want you to work out now is what's the uncertainty for the y now? No, it's not. It's not. And it's not square root of 10 either.
It is.
Let's do that.
Is it using the total and y?
Yeah, it is. Very good.
No, because of the square root
Doesn't-
power 1
It doesn't matter. So you can, if I give you a little hint, you can change y into x power a half. Now, I know you realise it's only one measurement, but you can imagine there's just a 1 here in front.
What is the average of y?
Well, I tell you the x we think is on average 2. So our best estimate for the y would be square root 2. That's usual. What's not usual is how we calculate the uncertainty.
Oh. No, we don't. We don't have the value. I mean, we don't have two measurements. Yeah,
What
if
is the error of 1?
Well, the error of 1, the uncertainty of 1. How uncertain are you that the number 1 is not the number 1?
25.
No, you can do better than that. No.
1 power 1 or 1 power 0 or 1.
0.
It can be 1 through 1 power 1 is 1.
Now hang on. You're thinking. It's good to think, but don't think too much. You can change this into two things. You can say this is the number 1 times x a half, and then how uncertain are you that the number 1 is actually the number 1 and it's not something else? You are 0% uncertain. You know the number 1 can only be the number 1. But the other way to do it is, and a sort of a sneaky way to do it, is to change this into x0, x a half. And then when you use the formula, you get 0 in the first piece, and then in the second piece you'll get a half. In fact, what I wanted you to see for yourself is that if you only have one piece, all that happens is you delete that piece from the square root formula. By the way, in case you're wondering, imagine Z equals A, B, C. Then the uncertainty of Z is equal to the average of Z square root A uncertainty over average of A squared plus B uncertainty over B plus C's uncertainty over C. Yeah, so if you only have two pieces, you have this. And then if you only have one piece, you have this. And that's actually what we have here. So let's have a look at it. The uncertainty in Y is equal to square root, I left out my Y average, square root, a half uncertainty in X over X average squared. So that's 1.4141 square root a half 0.010 over 2. Now what's nice is those guys cancel. So you're left with 1.4141 square root of 2 by 2 is 2, and then square root 0.01. So let me just hit that in. 1.4141 divided by 2 times square root 0.071. So back up here it's 0.071. So in other words, it's 71. No, sorry, 7.1 millijoules.
It's 3.54.
Yeah.
Did I mistype it?
Did you forgot the 1 over 2?
No, I don't think so.
You have forgotten the half.
You have forgotten the half.
What are you talking about? I included it. There it is.
And then
No.
the 0.0.
Hang on, watch and learn. 4.4141 square root dot times 0.010
Divided by 2.
over 2.
Square.
Oh, yeah, okay, yeah. Yeah. Approximately. What? Yeah. Nothing, yeah. 3.5, that's what I said. 3.5.
The funny thing is, he said, watch and learn.
I've learned something interesting. Okay, well, we can all make mistakes, despite how great we are. Right. 3.5 millijoules is the uncertainty here. Got that one? Right, here's another one now. Continue? Yeah. So here's the... Well, this is... Monica told me the wrong number there, so 0.0, yeah. 35. By the way, what is square root 10? It should be kind of close to this.
0.035 is not 3.5 millijoules.
It's not? Oh, did I leave out a 0 here? Must have been another 0 there. What's square root 10? Yeah. So you can see that you don't get exactly the same answer if you do what you taught of taking the square root of the uncertainty. That's because the relationship isn't as straightforward as that. Another example now. Here is an example. Question 6. Let's say you measure the frequency of something. You say that you think the frequency of a pendulum or whatever it is, we'll say is 4 hertz. You think in about 1 second, it should swing back and forth 4 times. But of course, when you were counting, you didn't get it exactly right, so you go 1, 2, 3, 4. Well, in a second, so it'd be like 1, 2, 3, 4. So you're not going to be exactly right. So maybe you think you could be off by as much as 0.1 hertz. My question is, what is the time, and of course the uncertainty in the time? Yeah, t equals 1 over f, yeah.
T equal 1 over f.
Is it using K?
No.
Like a what?
No. Oh guys, come on now.
1 over f.
Yeah.
Yes.
Yeah.
Oh, 1 side. Oh. Done. Oh.
X divided by
Yeah. Or even, you have a couple of ways of doing this. You could say t equals f to the minus 1. So the uncertainty in measuring t will equal the average t square root minus uncertainty in f over the f squared. So your t will equal 0.25 seconds plus or minus.
Teacher, I thought we only do like multiplication, division of the uncertainty when there has 2 uncertainty.
Why is minus?
Power minus 1. It's the last formula, Sean. No. You can use uncertainty when you're combining 2 measurements, or if you have a function acting on 1 measurement. It's a bit weirdly, but when I say combining uncertainties, I also include combining uncertainty with itself, a measurement with itself, which is another way of saying a function of the measurement. It's kind of like saying, if I measure x and I want to know the uncertainty of x squared, that's like asking what's the uncertainty of x by x. It's the same thing as x by y, it just so happens that y is the same as x. We got it here, Sean? Are you confused by this?
Why minus that?
Because it's the formula with the m and the n. I use this formula.
Oh.
Except, Sean, there's no y,
Yeah.
and the m is minus 1. That's the formula I used. Yeah. Right, let's calculate this. So it will be 0.25 square root squared minus fraction 0.1 over 4. So that's error is 0.0065 seconds. Okay.
So, what is average of
There it is there, 4 hertz. Yeah. Continue. One more example with multi-parts. Scroll down. Yeah. So let's have a look at something like this. We have t equals 2 pi root L over G. And we're going to use the t and the L to work out what G is. So step 1, I just want you to rewrite this formula so it's in the form of G equals. So just everybody take a minute to do that, please. Yeah. I just want you to rewrite this formula and tell me in the form of G equals.
4 pi square L over T.
Yeah, what's it? 4
Pi square
Yeah.
L over
over
T square.
over T squared. So I'll write it like this.
T minus 2.
Yeah? Yeah? So, what I want you to do now in part 2 is give me a formula for the uncertainty in your G. Can I borrow a calculator for a sec, please? Thank you. Okay. Did you get that? So what's the formula here?
4 pi
No.
Yeah.
No. Because, well, firstly you have the G average.
Yeah. Square.
Now, if you want to include this, you can kind of include it. So, if you were to look at, like, the 4 first, okay? Well, you've got to remember... Oh, sorry, I told Sean 4 pi squared was wrong, but actually it's right, yeah. So, sorry Sean, I apologise. Yes, the first thing you can do is take the constant out. So you have 4 pi squared. And then now we get the uncertainty. Yes, thank you Sean, which is the average G. And then root uncertainty L over L average. Yeah. Plus minus 2, yeah. Uncertainty T over T average squared. Okay, so one last thing now. Yeah.
Where is there?
Oh, sorry. There, yes. So what happens now is, let's imagine that this was for a grandfather clock, or some clocks where the L is fixed. So the L is fixed, you can't change the L. So somebody measured the L, and they measured it many, many times, and they think the L, they think is 1 meter plus or minus 1 millimeter. And then they took out a watch and they measured the time. And they did this many, many times, and they think that the periodic time is 2 seconds plus or minus 1 millisecond. Is 1 millisecond too small? No, we'll say they're very smart. So this is what they think the L and the T is. So, lastly, what I want you to do is estimate the G. I want you to give me the value they get, meters per second squared, plus or minus the uncertainty, which is meters per second squared. So to get this part here, you can just use part 1, because you know the L and the T. And for this part here, you will need to use part 2. Tell me what you get. And then, I'd say we'll finish after that. You'd have to calculate the G from here.
Is that average?
Well, yeah, because if you know the average L and the average T, you can work out what the average G is. Or rather, to be more precise with the English, if you have an estimate of L and an estimate of T, then you also can have an estimate of G from the formula.
So that's G average, sorry?
Yeah, I kind of use estimate and average the same meaning here, because in physics, to estimate something is to get the average. But if you want to be more precise with the English, it's G estimate, which happens to be the average, is equal to this formula, which you can get from using the L and T estimates. Did you get it? What did you get for the G?
9.87.
I'm like 9.
9.87.
Shh, indeed.
7.
Yeah. 9 point.
Keep the 6.
Yeah.
Okay, and let's calculate the uncertainty. So, what have we got? We've got 4 pi squared, isn't it? Yeah. Brackets, and then I got my previous answer, which is for the G, and then I have square root, and then I have that thing squared plus that thing squared, with a plus, and then here is the L, which is, what did I say, 0.001 over 1, isn't it? And then this one here is minus 2 times fraction 0.001 over 2.
Oh yeah.
Yeah. Now,
Yeah.
How this, I think, is a perfect example of how you can't treat uncertainty carelessly. Because look at this. We measured the length to be 1 meter, plus or minus 1 millimeter. Would you all agree that's very accurate? Like, I mean, how much is 1 millimeter compared to 1 meter? It's only 1,000. Yeah? You said the length is a meter plus or minus a millimeter. So that's 1,000. What's that as percent? That's a 0.1%. Or a tenth of a percent. What about the next one? A tenth of a percent. That was 1 millisecond in 2 seconds. That's 1/2000. That's a 20th, of a percent. So this error, uncertainty, is less than 1%. This one here, less than 1%. Much less than 1%. However, this is more like about, compare this to this, the plus minus is about 5%. So just really think about that. Here, this is plus minus less than 1%. Here is plus minus less than 1%. But here is plus minus 5%. You know, you would never have guessed this, that the error would combine so much to make a bigger error later. And that's why I said for the physics, uncertainty is very important, especially when you combine uncertain measurements. They can propagate in ways you can't expect. Now, compared to the chemistry, what are the calculations like? I mean, you said Lorraine gave you some worksheets you had to fill out. Were you doing similar things to this, or?
I don't think we have the average thing.
Yeah, but that's because you might use a different, like, percentage or something. Anyway, what I think would be great is if you can take this, which is just a summary sheet I typed up with the formulas, you have them in your notebook. I would be very curious to see how these compare to your chemistry. So maybe when you go home this evening, if you can compare this to your chemistry and see what is the same and what is different. I think most of it should be the same, though. 1, 2, 3. Yeah. What am I doing? I'm acting like it's precious or something. Thank you.